All right, welcome back. Today we're talking about absolute value. Now, when we learn about absolute value, typically we're kind of just, we begin with integers, right? We take the number line and we say the absolute value of a number is its precise distance from 0, right? So if I were to look at this real number line here and say, well, here's 0. I wanted to find the absolute value of 2. Well, I would say, well, it's precisely 2 away from 0. So the absolute value of 2 is 2. Now, what else has the absolute value of 2? Well, exactly one other number, -2. The absolute value of -2 is 2, because you can see that it has a distance of 2 from 0. You'll notice that this function is very symmetrical like that, right? The absolute value of 3 is 3, and the absolute value of -3 is also 3. I love when symmetry appears in mathematics like this, right? We see it with quadratic functions, we see it with these absolute value functions, and many, many other functions as well, right? So check this out. When we say absolute value of a number, we really just mean, well, it's like the size of the number, right? If I were to say that these orange squares were negative and these pink squares were positive, I could say that each of these represents, well, the size of the number, right? There are 2 of these, so the size of it would be 2. The size of this is also 2, right? This one happens to be negative, this one happens to be positive, but the absolute value of those numbers, right? The absolute value of -2 and the absolute value of +2 are the same, right? It's 2. Now, absolute value can be thought of as the size of a number. You could also think of it kind of as the magnitude. Now, another way of conceiving this absolute value is the distance. Distance from 0, right? We said on the number line, but you could also think of it as the distance as how far you had to walk from your classroom to the next classroom, right? There is no really positive or negative distance of walking, is there? You either walked a quarter mile in that direction, a quarter mile in the other direction, but the absolute value of the distance that you walked is going to be the same regardless of which classroom you were walking to and from. So, if I live out here all the way up in Vista, and I have to get on the road and take the freeway all the way down to here at SDSU, well, I had to drive about 37 miles or so. Now, if you were to ask me how far I drove, regardless of where I started, at home or at SDSU, well, I would say 37 miles, right? I wouldn't say, well, I traveled positive 37 miles there and then I came back negative 37 miles. No, it's just 37 miles both ways, that's it. So here's a nice kind of way of thinking absolute value is really just kind of like a distance. You can think of it's always going to be positive, right? So that's a nice way of being able to think about that. So when we see the words absolute value and you want to maybe write it down like symbolically, you might want to think something like this. We use these tall straight bars on the other side of x to indicate absolute value. Now, another way to be able to define this exact same function is in pieces. There are 2 pieces, and we could think of this really as a piecewise defined function, where if x is greater than or equal to 0, we just say, well, it's x. It's the absolute value of 3 is 3, right? But if x is less than 0, we want to take the opposite of whatever that number is, right? The negative version of that number. So if I were to say the absolute value of negative 3 is less than 0, so I would say negative 3, which is positive 3. So that's a really great way of being able to define absolute value in two separate pieces, depending on whether your input is positive or negative. Now you might be thinking, well, what if I have a bunch of stuff inside those absolute value bars, right? What if I have something like this? Then what happens? Well, we're still actually kind of just worried about when this inside the bars happens to be greater than 0 or happens to be less than 0, right? So if I wanted to find the absolute value of 3x minus 2, well, first off, I'd have to find out what the x value is, right? So why don't we just plug in a couple of numbers? So g of 4 is the absolute value of 3 times 4 minus 2. We'll close that absolute value sign. You could think of these almost as a grouping symbol, like parentheses. It's going to group everything inside together there. Now we have 3 times 4 minus 2, 12 minus 2. And we have the absolute value of 10. The absolute value of 10, remember, is just the distance that 10 is away from 0. So it's going to be 10, right? Every positive number that you take the absolute value of is just going to be that exact number. We would call that the identity function, as long as it's a positive number. Now, what happens, I don't know, what if we want to find g of negative 3? Well, I'm going to put my absolute value bar here and say 3 times negative 3 minus 2 and close that absolute value bar. And that's going to be 3 times negative 3 is negative 9 minus 2. So we want to find the absolute value of negative 11. Well, the absolute value of negative 11 is positive 11, right? It's 11 units away from 0. Doesn't, right? So we could also think of it as plugging it into this piecewise defined function. If I wanted to find the absolute value of negative 11, I would check here and say, well, negative 11 is less than 0. So I would find the opposite of negative 11, which is positive 11. So absolute values can also be represented graphically, right? So far, all we've done is some symbols, right? But what we'd like to do is say, well, yeah, we could graph it. Now, check this out. I graphed this nice function here, g of x equals x. That's just a 45-degree line straight through the origin, right? G of 1 is 1, g of 2 is 2, g of negative 3 is negative 3, straight up down the line, right? Now, why did I graph that? What does that have to do with absolute value? Well, if we wanted to graph this function f of x, the absolute value of x, think to yourself for a second. How are these graphs similar? Better yet, how are they different? Well, let's check it out. For every positive number, including as well as 0, I guess every non-negative number, you could say that this function and this function are going to be exactly the same, right? F of 1 is 1, f of 2 is 2, f of 100 is 100. So if I'm going to graph f of x in pink here, I'm actually just going to do some dashes right over the orange line. And say, wow, well, they fall right on top of each other. They're actually equivalent. But what happens to the left of 0? Well, the absolute value of negative 1 is positive 1, right? Because negative 1 is 1 unit away from 0. Same thing with negative 2 is 2. Negative 3 is 3. You may notice now how these graphs are similar, right? They're the same when they're positive or non-negative, but they are quite different when they're on the left side of 0, huh? It appears to me that we actually just took this line and snapped it, reflected it over the x-axis right here, right? If I were to take a mirror right on the x-axis, I would see that this line would flip, boom, and land precisely on this line, right? So the absolute value graph is this nice V shape with a sharp corner right here at 0. Now, sharp corners in graphs do come up quite a bit in calculus, which you're going to get to, right? So I'd like to just think, just for a minute, if I wanted to zoom in here. Zoom. We have a sharp, sharp corner right there. And this angle is precisely 90 degrees. Right? So there's no curve to this. It doesn't come down and curve and go like this. It comes down and sharply shoots to the right. Now, sharp curves on a graph can become very interesting, especially when you get to calculus.